Okay, so in this video, we are going to sketch the graph of the function y equals 4 root of x minus x. As always, we find the first and second derivative. If you want to differentiate root of x, think of replacing root of x by a power of x to the 1/2. And now you can differentiate y using the power rule. So y prime will be 1/2 times 4, so 2, x to the negative 1/2 minus 1, the derivative of x is 1, and y double prime will be power rule again, negative 1/2 times 2, negative 1, so negative x to the negative 1/2 minus 1, negative 3 over 2, minus the derivative of 1, which is 0. We have the two derivatives, and now when we look for critical or inflection points, we look for the derivative being either 0 or undefined. So we'll rewrite this so that the exponents are positive. So the derivative will be, if you send x to the denominator, the negative 1/2 becomes a positive 1/2 power, which is just root of x, so 2 over root of x minus 1. And the second derivative will be simply negative 1 over x to the positive 3 over 2. If you want to combine the first derivative as a single fraction, multiply top and bottom by root of x over root of x, and you'll have 2 minus the root of x all over root of x. And now we're good to go. Let us first find the zeros of y and the intercept. One thing to notice is y is not defined on the entire real line. Because of the square root of x function, we can only take the square root of non-negative numbers as we stay within the realm of real numbers. So the domain of our function is the non-negative real line. So it goes from 0 to positive infinity. Let's look for the zeros of this function. So y will be 0 for root of x minus x. Factor a root of x, and you'll get root of x times 4 minus root of x. And this is equal to 0 if and only if, well, either this term is 0, in which case x is 0, or this term is 0, therefore root of x equals 4. Therefore, if x is 16, root of 16 is 4, 4 minus 4 is 0. So this function has two zeros when x equals 0, when x equals 16. Let's look for the y-intercept. Well, we already have found this because when x is 0, y is 0, but when x is 0, this gives us the y-intercept. Let's just write it for good measure. Again, the y-intercept is the point where the function crosses the y-axis. Therefore, the y value of the function when x is 0. And as we have just found, x0 is a 0 of the function, which is clear if you plug in 0. 4 root of 0 is 0, minus 0 is 0. So the y-intercept is x equals 0, y equals 0. Let us now look for our critical points. And here it is interesting because if you look at the derivative, you have 2 minus root of x over root of x. And critical points, remember, are points where the derivative is 0 or is undefined. And we'll find that here, the derivative is undefined at x equals 0. So first, the critical points that satisfy the derivative is equal to 0. So the points where the tangent line is horizontal, so the curve is flat. Well, the derivative, as we have found, is a fraction, and a fraction can only be 0 if the numerator is 0. So 2 minus root of x would be equal to 0 if and only if root of x equals 2. Square both sides if and only if x is equal to 4. So x is equal to 4 is a critical point since the derivative at 4 is equal to 0. And it's a critical point of the type that the derivative is 0. Therefore, at x equals 4, the tangent line will be horizontal. But we have another critical point, which is different, coming from the derivative being undefined. Again, the derivative is a fraction. Both the numerator and denominator are defined for non-negative values of x, but we cannot afford to have a division by 0. So if x equal to 0, we have a root of 0 on the bottom, which is 0, and therefore the derivative is not defined. So y prime is undefined at x equals 0. So we have two critical points that are really different. At x equals 4, since the derivative is 0, the curve is flat at x equals 4. But at x equals 0, the derivative is undefined. Let us inquire, let us ask, how is the derivative undefined specifically? So we'll look at, since our domain is only for non-negative values, the limit of the derivative as x approaches 0 from the positive side. So let's see what happens to our derivative as x approaches 0 from the positive side. Well, x approaches 0 from the positive side. The derivative is 2 minus root of x over root of x. Let's look at our case. As x goes to 0, root of x goes to 0. 2 minus 0 is 2. Over, as x goes to 0 from the right, root of x will also shrink to 0 but always remain positive. So we have a 2 over positive 0 case, which gives us positive infinity. So you see, when we approach x equals 0, the derivative blows up. And if you think of it, if a derivative is infinity, or at least approaches infinity as x is approaching 0, well, the tangent line must be getting steeper and steeper and steeper. Therefore, around x equals 0, the tangent line will be almost vertical. Therefore, the curve will almost be vertical around x equals 0. So now we have our two critical points. Let's look for possible inflection points. And those will be coming from the second derivative being 0 or undefined. If you look at your second derivative, it is a fraction, and the numerator is constant, and it's equal to -1, so it will never be 0. So there are no points where the second derivative is 0, but at x equals 0, the second derivative is undefined. So x equals 0, so the second derivative is undefined. At x equals 0. So x is equal to 0 is a possible inflection point. Now, we will try and classify our critical points, being x equals 4 and x equals 0, but we already know what happens at x equals 0 because the derivative is undefined, and the second derivative is also undefined at that point. But what we know is that as we approach 0 from the right, since the derivative blows up, the curve will be more and more vertical. But we can at least classify, or at least try to classify x equals 4. And again, we classify a critical point. So this is a point where the derivative was 0, so the curve is flat there. The question is, will we have a local minimum, a local maximum, or something different? And this will be given by the second derivative. So we find the second derivative at x equals 4. So if we go back up, our second derivative is -1 over x to the 3/2. So we will get here -1 over x, 4 to the 3/2. Well, root of 4 is 2. 2 cubed is 8, and you get -1 over 8. We don't get it's -1 over 8, but that it is negative. because the second derivative at 4 is negative, the curve will be concave down. And so the curve is flat at x equals 4, concave down. So what we have will be a local maximum. So around x equals 4, for the time being, assume the curve is non-negative around x equals 4. Since the derivative is 0 at 4, the curve will be flat. And being concave down, we have a local maximum. So the curve would look something like this, around x equals 4. One thing is worth mentioning. If you go back to the two observations, our domain consists of non-negative numbers, and the second derivative is negative 1 over a positive power of x. So if you notice, for any x value that is non-negative, x to the 3/2 will be non-negative. So as long as x is positive, this number is positive, but the numerator is negative, so our second derivative will always be negative for any given value of x that is bigger than 0. So the curve will always be concave down. So we know we will have no inflection point. Concavity will never change because it will always be negative, therefore always concave down. Now that we have classified our one critical point and we know what happens at the other critical point, and that we know we have no inflection point, we can now, as always, construct our table of values. Recall that the function y is given by 4 root of x minus x. And we only look initially at the points of interest, the zeros, the y-intercepts, the critical and inflection points. We found 2 zeros when x was 0 and 16. At both of these points, y was 0. Then we found 2 critical points, x equals 0, which we already have here, and x equals 4. If you plug in here x equals 4, you have root of 4, which is 2 times 4 is 8, minus 4 gives us 4. And for inflection points, the only point that could have been an inflection point was where the derivative was undefined, which was x equals 0. So here we only have initially 3 points of interest. Let us now look at the sketch of our function. Here we don't need to sketch the negative part of the real line because we know that the domain of the function is on the non-negative real axis. Let's look at the 3 points. So we get 0, 0. Then we have the x, 4, and 16. So suppose this is 4. Let's go in slices of 16. This would be 8. This would be 12. This would be 4. And the y values range from, at least for our points of interest, 0 to 4. So suppose this is 2 and this is 4. And this is, as we've said, 4, 8, 12, 16. All right, so the first point of interest was 0, 0. The other point was 16, 0. So our 2 zeros. And the point 4, 4. So we have our 3 points of interest in the Cartesian plane. As always, we handle the critical points that we have classified. If you remember, the point 4, 4 was a critical point. And we had found that at x equals 4, the curve gave us a local maximum. So let's just copy this part onto the point x equals 4, y equals 4. So at x equals 4, we have a local maximum. The point 0, 0, if you remember, was, well, obviously the 0 of the function, the y-intercept, but more importantly, it was a point where the derivative blew up, right? If you remember, as we approach 0 from the right, the derivative approaches infinity, therefore the tangent line becomes steeper and steeper, so the curve will be getting nearly vertical as we approach 0. So we will connect this point with the value at 0, 0, but we know that at 0, the curve will essentially be nearly vertical. So the graph will look something like this. And here the curve, the closer we get to 0 from the right, the closer the curve is to being perfectly vertical. In the limit at 0, the curve becomes vertical. And above 4, there are no other critical points or inflection points. The only two critical points were 0 and 4. Therefore, to the right, the curve will never change its behavior again, since there are no critical or inflection points. Therefore, the curve is decreasing. It will be decreasing forever. The curve is concave down. It will be concave down forever, keeping in mind that we have x equals 16 as a 0. So here my curve should be a little flatter, because I have to reach 16, so it will look something like this. Okay, the only question is now, do we have any horizontal asymptotes? Well, clearly there are none on the left, because for negative values the function is not defined. Let's look at a possible right horizontal asymptote from the right. As x goes to positive infinity, what happens to y? The y value is 4 root of x minus x. Root of x is just the power of 1/2. And when we let x tend to infinity, we know the largest term will be the term with the greatest power of x, but x is x to the 1. So this is way bigger when x is big than x to the 1/2. This will be our dominant term. As x goes to positive infinity, negative x goes to negative infinity. So we do not have a right horizontal asymptote. As x gets bigger and bigger and bigger, the y values are getting larger and larger and larger and negatively. So the curve will keep being concave down decreasing to negative infinity as x goes to positive infinity. And so we have an accurate sketch of the function 4 root of x minus x right here. So finally, let us label what was special about these 2 points. This was just a 0, nothing special here. This was initially a local maximum, but if you look at the picture, we know it's more. At x equals 4, y attains its largest value of 4. So if you stay around x equals 4, the greatest value of y attained is 4, but nowhere else will you ever reach a value of y beyond 4. So not only is the point x equals 4 a local maximum, it is a global maximum. And the point here, x equals 0, y equals 0, was a critical point. And what was special about this point is that at this point, the curve is essentially vertical because the derivative blew up. So this is a critical point. Since the derivative at this point approaches positive infinity. So around x equals 0, the curve is nearly vertical. And now we have accurately sketched the graph of this function for its domain, which is the non-negative real axis.